Good morning, everyone. In this video, we're going to solve problems of chapter 7, where we have discussed the energy and the energy transfer. So let's start first with the first exercise. When a 4-kilogram object is hung vertically on a certain light spring that obeys Hooke's law, the spring stretches 2.5 centimeters. If the 4-kilogram object is removed, then the first question is, how far would the spring stretch if a 1-kilogram block is hung on it? And in part B, how much work must an external agent do to stretch the same spring 4 centimeters from its unstretched position? So let's draw this. Let's draw this spring. So in problem 15, we do have the following. So at equilibrium, the spring it has this position, let's say, okay? And then when we have a 4-kilogram block that is hung on it, they told us that the spring stretches by 4 centimeters. By, let me check, they stretch it by 2.5 centimeters, sorry. So from the equilibrium, from the unstretched position to the stretched position, we have this 2.5 centimeter, okay? So this is, let's say, this is the M1, block M1, and then this is the elongation Y1 of the stretched spring. Now, they said that if you remove this M1 and then you just put another object, you hung another object on the spring, which doesn't have the mass of 4 kilograms, but it has the mass of 1.5 kilograms. So let's say that in this case, you put another object that is M2, or yeah, let me just go a little bit further. So this is M2. And then the elongation from the unstretched position in this case would be Y2. So we want to check how much is Y2 if we put M2, if we hung M2 on the spring, how would be Y2? The problem is that we don't have the constant of the spring constant K. So that means that it's not easy for us to get the elongation Y2, and all what we have to use is the following given. So we know that for M1 equals 4 kilograms, we have Y1 equals 2.5 centimeters. And we need to check how much is M2 for M2 equals 1.5 kilogram. How much would be Y2? Okay, so to do so, we need actually two equations where in both equations we have the K, and if we have two equations with K, then we can eliminate K between these two equations. And actually we do have this kind of equation. So if you have a look at this mass M1, for example, let's start with M1. What kind of forces act on this object when it's hung vertically to this stretched spring? So we have first the weight, M1G, and on the other side we have the spring force, which is exerted by the spring on M1. It tries to push it up. So this is I would just call it F1 for the moment, but it's the spring force, right? So keep this in mind. And in the same way, actually, the block M2 or the block M2 or the ball, whatever, it is all subject to two forces. So we have M2G, and we have as well the spring force, which is exerted by the spring on the object M2, which I would call it F2. Now, don't forget that both F1 and F2, they are spring forces. And we have seen in the lecture that a spring force, we denoted by Fs, is given by, right? So the magnet is given by K times X, where X is the elongation. And we have a minus sign to say that this force opposes the elongation. So if the spring is stretched along positive X, then Fs would be an opposite in direction. So in this case here, we don't have the elongation along the X, but we have the elongation along the Y. So we can say that the spring force in our case here is equal to minus K times Y along the Y-axis. And so let's apply Newton's second law on both M1 and M2. So Newton's second law on M1, what does it give? If we just take the Y-axis to be, for example, upwards, right, like that, just to have one reference for us. So this is the Y-axis. And we can write down for Newton's second law, plus F1 minus m1g is equal to 0, because the object is in equilibrium. I mean, the spring has stretched by 2.5 centimeter. So F1 minus m1g is equal to 0. That means that F1 is equal to m1g. And that means, so F1 is equal to k times y. So we end up with k times y1 is equal to m1 times g. And we do the same for the block M2. So we end up with plus F2 minus M2G is equal to 0. So we can write down F2 equals M2G. And so we can write down then K times Y2 is equal to M2 times G. Now we have two equations, and both these equations depend on, so this is Y1, right? And this is Y2. Let me just write them correctly. So this is Y1 and this is Y2. So if we just divide these two equations, we end up with, so you just make a division of these two equations, we end up with Y1 over Y2 equals M1 over M2. And as you can see in this equation, we don't have the K and we don't have the G. So this equation only depends on the elongation Y and on the mass. And we want to get what is Y2. So we can just write down that Y2 is nothing else than M2 over M1 times Y1. And you just have to make the numerical application. So it's actually 1.5 divided by 4 multiplied by 2.5 centimeter, and you get the value in centimeter. So that's it for this first part. Now the second part, it was, well, we were asked to determine, so this was part A. Now in part B, the question was, how much work must an external agent do in order to stretch the spring by 4 centimeter? So if we have, again, unstretched position for the spring, so here's the spring again with its unstretched position, right? And we want to know how much work should be done by an external agent to stretch this spring by 4 centimeter. Y here is the Y actually, which is equal to 4 centimeter. So this is the question, right? Now we have seen in the lecture how we can actually calculate the work done by a spring force. We have seen that the work done by a spring force is equal to half K x initial squared minus half K x final squared, right? Where K is the spring constant and x initial and x final are the initial and the final position of this of the spring. So, but this is the work done by the spring force itself. Now, if we are looking for the work done by the external agent, okay, then this would be opposing in sign with actually to the work done by the spring force itself. And so we can write down W external is nothing else than half K x final squared minus half K x initial squared, where x initial and x final, they are the initial and the final position of the spring. So in this case, we don't have x, but we have y, because the spring is positioned vertically. So we have half K y final squared minus half K y initial squared. And we know that at the initial position, actually the spring was unstretched. So this is equal to 0. And so we end up with half K times y final squared. So we can deduce the K value from one of these equations, which we have derived in equation in part A. And y final, we know it's 4 centimeter. So we just have to do the numerical application, and this is what we get. So it is half K times y squared. K, we can get it from the first equation or from the equation Newton's second law for M1. So it's M1 times G divided by Y1 or X1. So I just call it x1, but it's y1, multiplied by y squared. So m1 is equal to 4. Y1 is equal to 2.5 10 to the power minus 2 because it's in centimeters, so we have to write it down in meters. And here it's 4 times 10 to the power minus 2 meters. And you end up with 1.25 joules. So this is the work done by an external agent to stretch the spring from its unstretched position by 4 centimeters, right? So that's it for this exercise. Let's go on with the problem 20. In this problem, we have a small particle of mass m is pulled to the top of a frictionless half cylinder, as you can see here. So this is our half cylinder. This is the mass m, and this mass is pulled up to the top of the half cylinder. So from this point here to the point here, by the means of a cord. So by a cord that passes over the top of the cylinder. So this mass is connected to a cord, right? As you can see in this figure, and this cord is pulled by this force F. Now, questions are the following. If the particle moves at a constant speed, you have to show that the force F, it has the magnitude m times g times cosine theta, where theta describes actually the position of the particle along this, this half cylinder. And they just give you a hint that if the particle moves at constant speed, make sure, or just don't forget that the component of its acceleration that is tangent to the cylinder must be 0 at all times. And this is, we know actually from the course, is that if you have a particle that is moving at constant speed within a circular path, then the tangential acceleration of the particle is 0. Because the tangential acceleration, it accounts for the variation of the modulus of the vector v. So it accounts for the variation of the speed. And if the speed is not changing, then there is no tangential acceleration. That's in part A. Now in part B, they asked you by directly integrating W equals integral of f dot dr, you have to find the work done in moving the particle at constant speed from the bottom to the top of the half cylinder. So that's it. Let's actually solve this problem now. In the first part, we have to show that F is equal to m times g times cosine theta. So let's take the particle at any place on this, at any location on this half cylinder. So let's take this, for example, is the location, which is arbitrary location, which corresponds to the angle theta between this position and the vertical line, right? And this line is just an imaginary line that relates the center of the cylinder to the particle m, and r is the radius of the cylinder. In order to get the value of F, or the magnitude of F, obviously we need an equation that accesses the forces. And the equation that accesses the force is the Newton's second law. So let's apply Newton's second law on the mass m. But before we do that, we have to specify all the forces that are acting on the particle m. So first of all, you all know we have the mass times g, so we have the gravitational force. We do have also the normal force, which is exerted by the cylinder on the mass. And as we have discussed last time, so you just have to kind of select the surface of contact between the two objects, which I just put here in dots. So this is the surface of contact between the particle and the half cylinder. And as we have seen, that the normal should be, first of all, in the direction of the object, because it's applied by the surface on the object, and it should be perpendicular to the surface of contact. So this is why we have n in this direction. So this is the normal. I'll just call it n, or let me just call it, yeah, whatever, n. And you have as well the force that is pulling this mass to the top, which is nothing else than the force F, because here you have a cord. So the force on a cord is the same. And so actually at any point, you know that this force F is just tangent to the half cylinder. Because actually, because the cord itself, it's along the cylinder or the half cylinder. So the force F, which is nothing else than the tension in the cord, will be tangent to the half cylinder. Now, if you apply Newton's second law on this particle m, you would end up with the following. Okay, just writing down Newton's second law, we end up with F plus N plus mg is equal to m times A. Now, to proceed, we have to specify two directions, as you know. We have to specify two axes along which we're going to project these forces. And of course, one of these axes should definitely, should be along the vector F, because we are looking for the force F. So what could be actually these axes? So you all know that in any case, whenever we have a circular motion, which is the case in here, when the particle moves from this point, from the bottom to the top, it's actually traveling along an arc of circle. So we can take, we know that we always have this centripetal acceleration. So we can take this direction to be the direction of the centripetal acceleration. We can take it as the x-axis. Okay, I can call it x-axis. And I should take another axis which is perpendicular to x, but which is also of interest. And the axis of interest in this case is the axis which is tangent to the half cylinder. So it would be this axis. It's tangent to the half cylinder, and it has the F along of it, right? So we are interested in getting the value of F. So this is why I'll just make the projection of the Newton's second law along the y-axis. And here, don't forget that you need to specify the angle between mg and either the x-axis or the y-axis. But as we have seen, if you have two axes which make an angle theta between them, then if you take the perpendicular to the first and the perpendicular to the second, then you would have the same angle between the two as well. And this is what I'm going to apply here. So the angle theta is between the radial line and this horizontal. mg is perpendicular to the horizontal, right? mg is perpendicular to the horizontal. That's the first line. And then we know the y is perpendicular to the radial direction. So this is the angle theta between mg and the y-axis. And let's now do the projection. So we end up with, along the y-axis, the projection produces plus f, okay, minus m times g. The projection of mg along the y-axis, it's over here. It's nothing else than mg cosine theta, because it's the adjacent to the angle. So minus mg cosine theta is equal to 0. Because actually along the y-axis, we have the mass times the tangential acceleration. And tangential acceleration is simply 0 because the mass is moving with a constant speed. So we end up with F equals m times g times cosine theta. And this is what we need to show. Right? So that is the first question. Now in the second question, we are required to calculate this work. It's the integral of f dot dr. So when you have bold characters like in here, that means that we're talking about vectors, which means that this f is a vector and the dr is as well a vector. So you have to use this expression to calculate the work done in moving the particle m at a constant speed from the bottom, so from this point B, or from point A, let's say, to this point B, from the bottom to the top. That's it. Yeah, so let's go on. Let's do it. So I'll just, okay, I'll use the expression they have, or they give us. So we have W is equal to the integral of F dot dr. Now, what is F and the dr? F is the force that is exerted on the object to move it, which is F here that we have derived. It's mg times cosine theta. And we need still to define or to specify what is the displacement done. Now, just have a look. When the particle is moving along this half circle, the displacement that is done is, you can call it whatever, it's called dr here, but we're going to see it by eye. So let me just remove this pictures and then I will just draw here. Imagine a particle is moving from this point or from any point from here, okay, to this new position, which is over here. Right, so it will actually be at two different angles. So it's gonna move from, let's say this is theta I, theta initial, and so this is theta I, and this angle actually would be theta I plus d theta, in the sense that we're saying that the particle has just done an infinitesimal, it has moved by an infinitesimal angle. And this is equivalent to the fact that the particle has moved an infinitesimal displacement, and this displacement is nothing else than this arc of circle, right? So this is what we mean by dr. This is the dr, right? So as you can see, but of course, I mean, here I have I have drawn it and a little bit zoom out, but in practice, I mean, this displacement is nothing else than just a point. So you move from this point to this point. So it's very, very small. But let's have a look at what is the product, what is the scalar product between F and dr. So if the particle is moving from this point to this point, we all have seen that the force F is nothing else than the tangential on the axis. So basically, this is the force F that is acting on the mass, right? This is the force F, and this is the displacement vector dr. Right? And if we take our axis that we have taken earlier, okay, just move it to over. If we take the x and y axis that we have taken, we see that, so we have taken this to be our x-axis, and we have taken this to be our y-axis, right? So you can see that both F and dr, they are both along the y-axis. They are along this y-axis, which is tangent to the half circle. So from this, we can write down actually that F dot dr, it's nothing else than, so dr is nothing else than dy. It's basically displacement along the y-axis, which is tangent to the half cylinder. And so F, it has the value m times g times cosine theta, right? So this is the vector F along the y-axis, so it's j. Scalar product dr times j, or yeah, along the y-axis. Now, how much is dr in this case, which is or dy actually? I call it dy. We'll see later on in further chapters, but I'll just explain a little bit here that if you have a particle that is moving along a circle, okay, you can define the angle of, so if your particle is moving from this point to this point, for example, right, this is its angle theta as we have in here. The particle, it actually is traveling an arc of circle S. And the angle theta is related to this arc of circles through the relation theta equals S divided by R, and R is the radius of the circle along which the particle is moving. So we want to apply this definition to our case in here. So in our case here, the particle has moved from this point to this point. The particle has moved by d theta. You see, it goes from theta I, from this one, to theta I plus d theta. And when it travels, when it moves by this infinitesimal angle d theta, it travels this arc of circle. So the one that we have seen here in red. So this arc of circle, instead of S, we have dy divided by the radius of the circle, which is R. So from here, we can deduce that dy is equal to R times d theta. And so we can, if we replace this by what we have in here in the expression, we end up with m times g times cosine theta multiplied by R d theta. And j times, vector product between j and j is just simply 1, because this is the unit vector. So if you want to replace this into the expression of the work, so we end up with m times g times R multiplied by cosine theta d theta. And here we should do the integration between the bottom point, so between this point, it's called bottom B, up to the point here T, which is the top. So between points B and T. Now, what are the characteristics of these 2 points? Actually, the characteristic of these 2 points are the following: is that so m times m and g and r, they are all constants, so we get them out of the integral. We have here cosine theta. So cosine theta is equal to cosine theta times d theta, and at the point B, theta is given by 0, because you know this line would be just at the surface, at the horizontal surface, so theta equals 0. And at the top, we have theta equals pi over 2. And all you need to do now is just to make this integral. So as you can see in here, the integral of cosine is nothing else than the sine. evaluated between 0 and pi over 2. So it's 1 minus 0. And so we end up with the value W equals m times g times r. So it only depends on the mass. It depends on the gravity acceleration. It depends on the radius of the half cylinder. And so this is it for this problem. We will move to the next problem. In this problem, a 2 kilogram block is attached to a spring of force constant 500 Newton per meter, as shown in the figure 7.10, which is over here. So the block is pulled 5 centimeters to the right of equilibrium and then released from rest. You have to find the speed of the block as it passes through equilibrium position in two cases. The first case, if the horizontal surface is frictionless, and the second case, if the coefficient of friction between the block and the surface is given by 0.35. So let's start with this problem. First of all, what we have to determine is the speed. So I've just here drawn a figure. So this is the first state of the system, where you have the unstretched spring and you have the block attached to it, which is over here. Now what happens is that we have stretched actually we have just pulled the block to the right of equilibrium, like we did in here, and then we release it from rest. What we are interested in is to get the speed of the block when it passes again through this position. So this is the equilibrium position, which is I'm just putting here, I'm drawing in red and in blue, in dashed line. So when the block, it passes again through this equilibrium position, what would be its speed? Okay, so since we are dealing with a problem where you have to find the speed, that means that we have to find some kinetic energy, right? I mean, the speed, it figures out in the kinetic energy, which is given by half mv squared. And we have here a problem where you have a spring. So one could think of the work kinetic energy theorem, because the work kinetic energy theorem, it gives access to the kinetic energy, right? W is equal to delta K. So if we know what is the force, what's the work exerted by the force acting on this block, and we know what's the expression of the kinetic energy, then we can get the speed when it passes through its equilibrium position. Now we need two positions actually to start this problem. So the first position would be the initial position when the block actually was 5 centimeters from its equilibrium to the right. And at this position, we know that Vi is equal to 0 for the simple reason that the block was released from rest. And the final position that we are looking for is this one, is at the time when the block, it passes through this equilibrium position and where it has this speed V. So we call it V initial is equal to 0, V final is equal to the value that we are looking for. These are the initial and the final state of the system, and we are going to apply the work kinetic energy theorem, W is equal to delta K. So what are the forces acting on this object? So whenever the object is sitting on this surface, you have definitely, so you have the mg, or let me just draw it in here. So you have the mg, the gravitational force, it's the weight, you have the normal, which is applied by the surface on the block, which is given by n. It's perpendicular to the surface of contact between the block and the surface. And you also have the spring force, which is exerted by the spring on the block, and which always try to get back the block to its equilibrium position. So this is the spring force Fs. Now the question is, what else force, what do we have forces, other forces that act on this block? Well, the forces that act on this block depends on the surface. If the surface is frictionless, then these are the only forces acting on it. If there is a friction between the surface and the block, then there will be also some frictional force. So let's start with part A. In part A, we don't have any friction. So these are the three forces acting on this block. And so therefore W, it is given by W of the spring force plus the work done by the gravitational force. I just call them Ws, Wg plus the work done by the normal force. Those would be equal to delta K. The work done by the gravitational force and the work done by the normal force is simply equal to 0, because these two forces, they are perpendicular to the displacement done by the object. So we are only left with Ws is equal to delta K. And we're going to see how much is these two quantities. So and what concerns the delta K is the difference between the kinetic energy in the final state and the initial state, right? So delta K is nothing else than half m v final squared minus half m v initial squared. So v initial is equal to 0 because the block is released from rest. So we end up with half m v final squared. That's it. And v final is the variable we are looking for. So we only need now to do or to evaluate the WS. So WS is the work done by the spring force, and we have seen actually in the course that the work done by the spring force is equal to half kx initial squared minus half kx final squared. So half kx initial squared minus half k x final squared. And actually, in the final position, we know that the object will pass by its equilibrium state, which means that in this final state, the spring is unstretched, which means that x final is equal to 0. And so we're only left with half k x initial squared. So from here, we can write down half k x initial squared is equal to half m v final squared. And so from this equation, you can immediately deduce the value of v final. So as you can see in here, you end up with v final equals square root of 0.625. And so therefore v final is equal to 0.791 meters per second. So this is it for this part. Now we're going to move to the part B. So in part B, we do not only have these forces, but in addition to the three forces, we do have the friction force. So I'll just move downstairs here. So we have in this case, we have in addition to WS, WGWN, we have WF, which is the work done by the friction force. So again, WGWN, they are equal to 0 because both forces, the mg and n, they are perpendicular to displacement. And again, v initial squared is equal to 0, so we are left with WS and WF. WS won't change. It's the same as we have calculated in part A, over here. So it's given by 0.625 joules. And what concerns W of the friction force, so the friction force, it acts in the opposite direction with respect to the displacement. So the displacement is happening in this direction, in the same direction as the spring force. So this is, let's call this is delta X, right? And so the friction force, it opposes this delta X. So the work done by the friction force, as we have seen in the lecture, it's given by the friction force itself, dot, so scalar product with delta X. Now, what kind of friction force we're talking about? Of course, we're talking about the kinetic friction force because the object is already moving. So we are in the situation where the friction force is kinetic. It's not static. But have a look. So the scalar product takes into account the angle between the two vectors. And as you can see here, the angle between these two vectors is given by 180 degrees. So it's pi. And this is why W is nothing else than minus the friction force multiplied by the modulus of delta X multiplied by just Fk times delta X times cosine the angle of the two, which is pi. And so this is why it's equal to minus Fk multiplied by delta X. And so we have everything now. We have the, Fk is nothing else than mu k times n, the normal. And if you just apply Newton's second law on this block along the y-axis, you end up with the normal equals to mg. So this gives minus mu k times m times g multiplied by delta X. And that's it. So you have the equation where the only unknown is v final squared, and you end up with v final equals 0.531 meters per second. And as you can see, I mean, as expected, the velocity or the speed, it has a magnitude which is smaller than in the first case, because here you had a friction. So part of the energy of the block is transferred into heat because of the friction force. So this is it for this problem. In this final problem, we have a skier of mass 70 kilograms pulled up a slope by a motor-driven cable. The question is, how much work is required to pull him a distance of 60 meters up a 30-degree slope, as you can see in this figure, which is assumed to be frictionless at a constant speed of 2 meters per second. So this is the first question. And the second, what would be the power of a motor that is required to perform this task? So let's start with part A. So this is actually our inclined plane. It's inclined by an angle theta of 30 degrees, as you can see in here. So this is the skier, which is actually connected to a cable, and this is the motor actually, which is pulling it up. Okay. Now, in order to determine the work that is required to pull him a distance of 60 meters, so this is the displacement along the inclined plane, we have to check all the forces acting on this skier, and then the best would be to apply the work kinetic energy theorem, because in this case we can access the work of all forces acting on it. So what are the forces acting on the skier? So you have first the mg, right? This is the gravitational force. You have the normal force that is exerted by the surface on the skier, and on the other side also you have this the tension in the cable. But the tension in the cable is nothing else than the force exerted by the motor. So this is what we call it Fm, which refers to the force exerted by the motor. And so now let's apply the work kinetic energy theorem on this case. So as you know, the work kinetic energy theorem is given by W is equal to delta K, right? But let me start with the second half of the equation. So delta K is given by half M, so V final squared minus V initial squared. But actually they told us that we want to pull him at a constant speed, which means that V final is equal to V initial, and that gives us 0. Now, all what we need to do is to determine how much is W. So W is actually the summation of all forces acting on this system, on the skier. So you have W of the motor, of the force exerted by the motor. Then you have WG, which is the work done by the gravitational force, and you have the work done by the normal force, right? So all these forces, they act on the skier, and so the total work done on the skier would be the summation of all these works. Now, let's actually specify the displacement. So the displacement is, let's say that the skier moves from this point up to this point, for example. I mean, let's say it makes this kind of displacement. So this is the D. This is the displacement vector. Let me call it delta X, or D, doesn't matter. So this is the delta X, which is the displacement of the skier from the initial point to the final point. So we are going to determine the work of each of these forces based on this displacement. Let's start with the normal. So the normal, it's perpendicular displacement, so it produces 0 work, as we have seen in the lecture. Fm, we cannot calculate the work Wm by simply making the scalar product between Fm and delta X, because we don't know what is the expression of Fm anyway. So Wm, we cannot calculate it. We have to deduce it from this expression, from the W equals delta K. But Wg, we can calculate it actually. So Wg is the work done by the gravitational force, right? So if I just make another figure around here, and in order to calculate the work done by the gravitational force. So here is your skier. So this is the point, right, we are looking at. Here's the skier. This is the angle theta. This is mg, right? This is the gravitational force. And this is the delta x. These are the two vectors we are looking at in order to calculate Wg. And we know that Wg is the scalar product between mg and delta x, because mg is this constant force. So it's mg dot delta x. Now, that is given by m times g times the displacement, let's call it, it's a distance d, times the cosine of the angle between the two. So what is the angle between mg and delta x? Have a look. If I just draw here a horizontal line, you would see that this is the angle theta, is the same as the angle theta in the inclined plane. And you have here an angle pi over 2. So the angle would be here, then we end up with cosine pi over 2 plus theta. And actually, if you just search back the relation between trigonometric functions, you can conclude that cosine pi over 2 plus theta is nothing else than minus sine theta. So minus mgd sine theta. This would be the expression of wg. Right? So wg is equal to this expression, right? Wm is what we are looking for, and we know that W total is equal to 0. So we end up with Wm minus mgd sine theta is equal to 0. And so Wm, the work done by the motor, is nothing else than m times g times sine theta multiplied by d. So I just replace each term by its value. The mass, the gravity, theta is known, and displacement is known. So you end up with 20.6 kilojoule. So that's it for the first part. Now for the second part, a motor of what power is required to perform this task? So we need to calculate the power, the power of a motor that could really perform this task. And we know what is the definition of the power. So we have seen that the power is nothing else than the work divided by the delta T, the amount of time needed. So we don't have the time. They didn't tell us how much time is needed to pull the skier along this inclined plane, but actually we know that the skier is moving with a constant velocity. And so we know that we know how much is the speed, we know how much is the displacement. So we can use the expression or the definition of the average velocity, which is given by v equals delta x over delta t. V is known, delta x is known, but delta t is the unknown. So we can conclude that delta t is delta x over v. So it's given by 30 seconds. Now, all what we need to do is just to replace w and delta t by their values. And so we end up with the power equals 20.6 kilojoule. So 10 to the power 3 joule divided by 30 seconds. And we end up with 686 watts. So that's it for this problem.